let's now do what? Let's now do the probability current. Okay, so the probability, this is the current. The probability current. Now, when we check the probability current, why it matters? Because it's the interpretation of probability as a probability density. Okay, so that means that a psi, square modulus of psi, is the probability current, and or we can say it as a probability density. Okay, it's the same. Now, for this interpretation to work, we have two conditions. The first condition, that the density must be positive. That means the probability should be greater than 0 or equal, and greater than or equal, and that makes sense. That's the basic human sense. It's a probability, so it cannot be minus, right? And two, the density again must be conserved, and that means it obeys the continuity equation, which is partial sub t rho plus j equals 0. J equals 0. This let's now check the Klein-Gordon and Dirac. So for Klein-Gordon, we take what? We take the equation, and Klein-Gordon in the basic form is like this. We don't really care about sub what or whatever these stuff are. Not important right now. This is the basic form of Klein-Gordon, and this is the real form, and we take also the conjugate form, and the conjugate form is psi conjugate. Okay, now to check, we said it's the square modulus, right? We multiply this by the conjugate, and we multiply this by the normal, the psi. So now we have the second derivative square. Now this would be, I'm talking about this, is equal 0, and for this we have psi square psi conjugate is equal 0. Now let's subtract. Okay, so we can cancel the m. Okay, what we end up with? We end up with psi conjugate partial square psi minus psi partial square psi conjugate equals 0, and this is the total divergence, right? So we expand. Remember that partial square is what? Is partial mu. Okay, so what we do now, we substitute. So we have psi conjugate partial mu psi minus psi partial mu psi conjugate is equal what? Is equal 0. And if we factorize this guy here, we get what? You can figure it out without the minus psi is equal 0. And this one is, if we define the current J mu as I over 2m psi conjugate partial mu psi minus psi mu or psi conjugate, this is the current. And so this satisfies what? The partial mu J mu is equal to 0. Okay? It satisfies it. So the first condition now, the density is positive. All right. We checked this one. We checked the second one, if it's conserved or not. Now let's check the density. Now the density, what we do? Rho is what? Is J0. That means what? That means rho is equal I over 2m of what? Of psi conjugate partial t psi over psi minus partial conjugate over t psi. And what is psi? Psi is the plane wave, remember? So it's the normalization, this is n, okay? The normalization factor n, e times e to the power I e t plus ip dot x. And by that we can see that partial psi or partial t is equal minus I e psi, and partial psi conjugate or partial t is equal plus I e psi conjugate. And if we substitute in here, what we will get? We get that rho is equal. Now let's substitute. It will be I over 2m. We open the box. We have here psi conjugate from here. We put it, and we have the partial psi, which is minus IE over psi minus what? This guy here is plus IE, and we have psi from here. Okay, this equals what? This equals same over 2m minus IE, and we have here minus IE, and I feel like I forgot something. Yeah. Yep, there's conjugate here. I forgot to put it. Okay, so now we have what? If we factorize, psi conjugate psi is equal psi square modulus. Remember? Alright, so we have now psi square modulus here. And by now we have rho is equal I over 2m. We have now minus 2IE, and psi, if we put this psi here, and times the conjugate, the exponential will cancel out, right? So we will end up with what? With n squared, the normalization factor. So it will be, and E2 goes with 2, and we end up with rho for Klein-Gordon equals E over m times square modulus of n. Now, here's the thing, right? Rho can be negative. That's the problem. The problem that rho now can be negative. And that's a problem. A negative probability makes no sense. What is the consequences of having a negative probability? That means we cannot interpret rho as a probability density. So, the problems we have, the consequences, we cannot interpret rho as probability density. Second of all, must reinterpret rho as a charge density. So we must reinterpret rho as a charge density. And finally, negative rho corresponds to opposite charge. Why did I put y? Opposite charge, which is anti-particle. So now we know the problem with Klein-Gordon. Okay. What about Dirac? Well, let's now start from a Schrödinger equation. Schrödinger equation of a relativistic type, it's the combination of Schrödinger equation and Dirac. And what is the difference? We know that the Hamiltonian now for Dirac, Hamiltonian of Dirac, is equal that alpha rho plus beta m. Sorry. That's the Hamiltonian. So if we substitute it in Dirac, we will have what? We will have that I partial t psi equal h psi, which is equal alpha dot p plus beta m over psi. So if we take the Hermitian conjugate, which is the adjoint of the, we have now minus I partial t psi the conjugate, or we can now say it as a dagger, equal psi dagger Hamiltonian dagger, which is equal psi dagger Hamiltonian. Okay, why we do that? because this guy here is Hermitian. And Hermitian means that if we, let's explain it here. Hermitian means that if alpha I dagger equals alpha I, not if, I mean alpha I dagger equals alpha I, or another term, alpha dagger equals alpha, and beta dagger equals beta. That's what Hermitian means, mathematically. I'm talking here mathematically. So now we have it here. So we have now minus I partial of partial t psi dagger equal psi dagger Hamiltonian in a way or another. Okay. So we know that rho is psi dagger psi. And we want to calculate the partial t rho. Now, partial rho, partial t, partial psi dagger, partial t psi plus psi dagger partial psi of partial t. This is what? We only calculating the rho. Okay, so if we take this equation and we take the first derivative of it, we will have this one. Okay, so now partial rho over partial t is equal what? Is equal, now if the partial of partial t is equal the Hamiltonian, the energy, the operator, if we add I here and we said I h bar, it will be equal this one. Sorry, it's I partial of partial t is what? The energy, which is the Hamiltonian. Okay, so partial of partial t will be equal I h bar. Sorry, h Hamiltonian. There's no h bar. So I psi dagger Hamiltonian over psi plus psi dagger from here, from this guy here, partial psi over partial t is again what? Minus I h bar psi. All right. Now, the first derivative of rho with respect to time now is, we have to express these guys here. So it's like we're saying I psi dagger h bar psi minus I psi dagger h bar h. I'm saying h bar, it's Hamiltonian, I'm sorry, and psi. Okay, but we know that the Hamiltonian here is what? Is this guy. And if we take the derivative for time, this won't be exist. So it will be I psi dagger alpha momentum psi minus I psi dagger alpha momentum psi. But momentum, the momentum is what? P is I nebula minus I nebula, and it acts on the right, correct? So if we substitute the P, we'll have alpha dot minus I nebula acts on psi minus, and we have minus I here, and we have minus I inside. Nebula acts on what? I feel like, yeah, this is dagger. Acts on what? Acts on psi dagger dot alpha psi. So now we have psi dagger alpha dot psi, because this guy and this guy goes away, we multiply it, and we have nebula psi plus what? Plus also, because this minus goes as a plus. Now we have plus nebula psi dagger dot what? Dot alpha psi. And now we can take the we can factorize the nebula. So we mean nebula times dagger alpha psi. Now we, as mentioned before, the continuity equation is partial rho or partial t plus nebula j equals 0. And we know that rho is equal psi dagger psi, and j is equal, from this, if we compare it, will be psi alpha psi, psi dagger alpha psi, right? So it's exactly the equation, because here we have what? We have partial rho, partial t. We have also here partial rho, don't to forget, and same here, right? So it's the equation we have here. So partial rho or partial t is always, it's positive. That means that rho is always positive. That means that rho is equal psi dagger psi, which is psi 1 squared plus psi 2 squared plus psi 3 squared plus psi 4 squared. So the sum of the squared magnitude is always positive. This is automatically validate the density. So the density is valid. The density is always valid. No need to reinterpret the charge density or anything. It works as a probability directly. So to sum it up, what we have been talking about, let's talk about the let's see. We have here what? We have the Klein-Gordon, we have Dirac. For the density, in Klein-Gordon, rho is equal to E over m psi square modulus. For Dirac, rho is equal rho dagger psi dagger psi. For the sign, can be negative, positive, and let's say negative. But for Dirac, it's always positive. Okay? The interpretation here is a charge density, and here is probability density, which is what we want, right? Here for E less than 0, rho is less than 0, which is antiparticle, and here rho is greater than 0. This is what Dirac's main motivation. Find an equation with positive definite probability. So in this way, we managed to see the main difference between Klein-Gordon and Dirac from scratch up to probability density. Thank you.